damaging question. How do you reckon you're elite, merely brandishing weapons? This is your career or life support. And we're not white hats trying to write reports. Any box can be popped with the right resource. So your threat model's worthless. Nice report. We got your network on life support. Yeah! Fuck your firewall trying to hide your ports. We hop these through proxies to hide the source. So your packet logs nothing. Nice report. Nice report. Yeah. What up to Concrete, my producer, man? #1 in the game. This goes out to my crew, Soft Say. This goes out to Visigoth and all the Ken Shoto, man. This goes out to the Sin Crew. This goes out to RFP, Toby, Sharky, and Abe, man. Stare. This is when the buzzwords make you elite.
Hypervisor Web 2.0 Ajax cross-site request packetry marking.
Too many buzzwords, black and white hat. Too many hype jacking wannabes at DEF CON like that. Too many white fat industry pipe raps. Real hackers out hijacking your WiMAX. Too much click bullshit in politics. Too many props for sites hit with JavaScript. Too much of the media acknowledges bullshit hacking, perpetuating novices. Too many phones wiretapped without impunity. Too many granted retroactive immunity. Too much peacocking in the InfoSec community. Between kids comparing the favorite flavors of Unices. Too many hackers deserve inadequate eulogies. Forgotten to burn, reminiscing how it used to be. I don't let this type of shit get to me usually. I can't be complacent, I have to save it. This is your career or life support. And we're not white hats trying to write reports. Any box can be popped with the right resource. So your threat model's worthless. Nice report. We got your network on life support. Yeah! So fuck your firewall trying to hide your ports. We hop these through proxies to hide the source. So your packet logs nothing. Nice report. Nice report. Open the mic wire, flip a beat to the speakers, and watch me light fire to this industry's hype whores and hype biters, reporters and typewriters, making dock raid resort to blow torches and vice pliers, spiked wire, shit, C4 and battle axes. Put me on a keyboard to battle haxes. Sheepish and claiming beef. Cattle hackers talk shit, get owned by me and tattle after. The skills of these new kids useless. Exploits, they can't write their own excuses. Just download exploits and rootkits. And now you think you're worthy the status of Dave Murphy? A ninja's not defined by his sword, of course. And there's more to a network than a switch and a cord. So I retort and ask an ego-damaging question. How do you reckon you're elite, merely brandishing weapons? This is your career or life support. And we're not white hats trying to write reports. Any box can be popped with the right resource. So your threat model's worthless. Nice report. We got your network on life support. Yeah! Fuck your firewall trying to hide your ports. We hop these through proxies to hide the source. So your packet logs nothing. Nice report. Nice report. Yeah! What up to Concrete, my producer, man? #1 in the game. This goes out to my crew, Soft Say. This goes out to Visigoth and all the Ken Shoto, man. This goes out to the Sin Crew. This goes out to RFP, Toby, Sharky, and Abe, man. Steric, the 0x41 crew. I say what up to Satori, Subroot, Frederick Diggle, Doc Brown, Atlas, the Janus group, man. What up to all my homies? Doc Ray, 2009, the world is mine. Nice report. This is when the buzzwords make you elite.
Hypervisor Web 2.0 Ajax cross-site request packetry marking.
Too many buzzwords, black and white hat. Too many hype jacking wannabes at DEF CON like that. Too many buzzwords, black and white hat. Too many hype jacking wannabes at DEF CON like that.
All right, I had to get some music going. RJ was giving me a little trouble yesterday for not having any anything happening when people first signed in. Get my sound turned off there. So welcome back, everybody. We're going to get into defense today. And just trying to make sure I've got everything streaming properly. Got the room chat up. And just trying to get into where I can manage my stream. Give me 2 seconds. All right, there we are. And I can see the chat. We have 4 concurrent viewers. We're good. Welcome back, everybody. Let me get the agenda up. Show you what we'll be talking about today. So today's obviously day 3 in our journey through network foundations. We've talked about, I guess, the true foundations, which is OSI model, binary, subnetting, V4 versus V6, anycast, multicast, etc. We got into switches and routers yesterday, talked a little bit about spanning tree, we talked about DHCP, first hop redundancy, and routing. So which brings us to today. We'll talk about secure management, DNS, DNSSEC, DNS crypt. We'll talk about PKI. So just working with digital certificates and certificate authorities. We'll talk about firewalls. We'll talk about VPNs. We'll talk about .1x a little bit more. We'll get into the guts of IPsec, as well as TLS. So who was that? Love it. That was, if you search for SophSec, S-O-P-H, I'll type it here, S-O-P-H-S-E-C. It was called Nice Report. Had some hardcore gangster nerd rap to set the tempo. Yeah, Nice Report. This is probably, it's like 8 years old, 10 years old, but none of those guys get enough play, so go give them some attention. Tomorrow, we'll be talking about the attack surface. We'll be doing that from the basement down at Neon Temple. So if you can come out. If you can tune in. And then, of course, on Saturday, we'll be doing the all-day workshop. I think there's about 8 or 9 people signed up right now. I think we've got room for at least 20. So if you can make it out at any point during the day, come on out. I'm sure we'll have room for you. And with that, let's just jump into some layer 2 defense stuff. So I'm reusing some slides from a Cisco course that's since been removed. They don't have this course anymore, but a lot of the slides and the technologies they talk about are super practical still. So don't think that this is outdated. Maybe some of the commands have changed or the devices have changed, but the concepts are still the same. So we talked about STP yesterday, right? The spanning tree protocol. And this is something that Cisco runs by default. And it's not something that everyone runs by default. And it's, like I said, sometimes you'll turn it off in a really large environment, like in a university. Other times you'll have a stack of equipment from a vendor that just doesn't turn on spanning tree by default, and you don't know until you create that loop. And of course, if we create a loop in a spanning tree environment, or I should say if we create a loop in a layer 2 domain, everything is just going to come crashing down around us. You'll lose your phone calls, you'll lose your IP cameras, you lose whatever you have that are network-based services. So while we are talking foundation and defense and offense, it's my belief that everyone coming through the class is really kind of the mindset that we want to defend the networks, we want to make them stronger, we want to make them more resilient. So spanning tree is one of the first points we could look at, kind of working up the OSI model, right? We start at layer 1, we said somebody can cut the wire, jam the signal, we're in trouble. Okay, we've accepted or we've mitigated those risks. Now what do we start thinking about at layer 2? And that's where you get into your discovery protocols, you get into ARP, you get into spanning tree. So that's what we're going to focus with starting off today, is just kind of that layer 2 security from the OSI model. So in this environment, they just have the 2 switches. The 2 switches, however, are configured in such a scenario so that there is actually a loop. And if you didn't have spanning tree enabled, you'd have a broadcast storm. Assuming that you have spanning tree, everything works just fine. So why does it work fine? Well, we come up with this idea of a root bridge. And the root bridge is really the center of the network. This is the center of the universe as far as spanning tree is concerned. And then everything else, once you know who the root is, all the other devices just figure out how to get to the root. So when switches first boot up, they start sending out these messages that we talked about yesterday called Bridge Protocol Data Units, BPDUs. And these are the normal messages of spanning tree. If you were to sniff with Wireshark and your environment runs spanning tree, there's a good chance you'd see this message. It comes out every 2 seconds, so they're real common. The BPDU includes the priority of the switch as well as the MAC address. And let's see, I wonder, wonder if I have BPDUs. I'm plugged into kind of a junky switch. I talk all this crap about other people's switches, and I just look down at the floor, and it's this little like $20, $30 HP 8-port gigabit switch. So I don't think it does any spanning tree whatsoever. But the upstream device may actually do some spanning tree. So I'm just kicking off a Wireshark update. You know what? I'm not. Let me just launch Wireshark without the update. And we'll just go ahead and we'll capture on our Ethernet link, and we'll just type spanning tree in the filter. Slide this down, give us some room. There we go. Stop. Very cool. So this actually works out perfect. Let me come over here. I have a crummy Soho router from Spectrum that I'm about to replace, or from Frontier, I guess. This is about to be swapped with another one. It's the first time I've had a Soho router my whole life. These are crazy times. Behind that, I've got a Cisco switch, which allows me to do some cool stuff that the Soho router wouldn't. And then behind that Cisco switch, up in my office, I've got a little wacky HP switch with 8 ports. And you know what? It's allowing this class to run, so I don't want to make fun of it too much. I'm pretty happy with my HP switch. And then here we are on this computer doing a stream. So my Cisco switch is sending out these bridge protocol data units every 2 seconds. When they come into the HP switch, it's not running spanning tree. So it's not really thinking about it. It just gets that message, and it goes ahead and it floods it out this interface. So if I jump back over to Wireshark, we can see at 0.5 seconds into my capture, there was a BPDU. Then notice at 2.6, 4.6, 6.6, right there like clockwork, every 2 seconds BPDUs are being sent out. So just by sniffing for 2 seconds, we can go, okay, spanning tree is in this environment. What else do we know? Well, if we look at the source MAC address of those frames, that's a Cisco switch sending them. We know because the first 24 bits. It says Cisco, but really Wireshark is just being kind to us, and it's taken this string, B8621F, and it's converting it to the word Cisco to let us know that's a Cisco prefix. When we come down here and we look at spanning tree, you see some operations. We see that it's a configuration BPDU. Here are the flags. Here's our root ID. Whereas like the root of spanning tree is this device. My ID is this device. It's like, oh, cool, so you are the root. Additionally, when we look at this, we see 32768. That's your priority. Then it's followed by a MAC address. So just to kind of reiterate this, every 2 seconds BPDUs are going out. Their configuration messages. It contains a bridge ID, and whoever has the lowest bridge ID becomes the root. In this circumstance, here we see who the root is, and if we notice the BPDU before it, it's actually just us. So that's kind of cool. If we come back to our slide, let me minimize Wireshark for now. They're showing us, oops, come back here. We're looking at this switch on the left, and notice it has a priority of 8192. Someone artificially, or just administratively, lowered that priority. This switch would be 32768 by default. So it sends BPDUs out, the other switch sends BPDUs out, we compare the priority numbers. Whoever gets the priority lowest wins. If it's a tie, the lowest MAC address wins. So let's talk about that for just a second. So in a lot of environments, people run spanning tree and they're not thinking about it. If you're not thinking about it, it's on by default. You're sending out these messages with the priority 32768. If everyone does that, who winds up being the root of spanning tree? The one with the lowest MAC address. So based on what we know about MAC addresses, the IEEE assigns the OUI, or that first 24 bits of a MAC address, to each vendor that comes along and wants to make Ethernet devices, right? They're handed out in order, chronologically. So what happens is when everybody's doing spanning tree the same, the device that wins to get to be the root bridge is the device with the lowest MAC address. Well, if MAC addresses are always higher on newer devices, it means that spanning tree is selecting the oldest device in your company, potentially, to be the center of the universe. That could be pretty dangerous. And not just dangerous, I guess dangerous is like too sexy of a term for it. it could be very, very wasteful. I'll show you kind of a cool company that I worked with for a while. They had big Nexus 7000s, very expensive. I think they paid, the way they were equipped, maybe around $100,000 per switch. And when we hook these switches together, we use 10 gig ports like this, but the way that the line cards were built, when you used one 10 gig port and you wanted a full 10 gigs, you wanted to use all of it, you couldn't use the 3 ports next to it. They were just a wacky generation of line card. So I had to burn a bunch of ports to get a 40 gig ether channel between these two switches. And this is basically like the backbone between my 2 core switches. Well, what happens is you come up here and you go to various like top of rack switches, distribution switches throughout your data center. And then these come down to a chassis. So when we think about a chassis can hold blade servers, which instead of being a rack mount server, these just look like a cartridge. And they get the power, they get their Ethernet, they get all their connectivity and management from a backplane. There's no wires. All the wires go into this chassis. And lots of vendors make chassis. Cisco chassis, Dell chassis, HP chassis. These folks had Dell blade servers, and they had a Cisco switch that went in the back of the blade server. So the blade server chassis had a switch built into it, which is kind of neat. It just so happened that this was the lowest MAC address in the data center. So what happened? This was the root of spanning tree way over here. And the way that spanning tree works is that it's loop prevention. So if we look at core 1 and core 2, they go, what's the fastest way to get to the root bridge? That way. Well, this is just a 10 gig link. And what got put into a blocking state? This big 40 gig port. So this is how the network was designed to work. Not the spanning tree part of it, but the physical topology. We had all the cabling right, or at least they did. This was existing before I got there, but nobody thought about spanning tree. Because spanning tree selected this device to be the root, the way that the cancellations worked to break, to basically break loops, is it went on some really fast links between pairs of equipment and then put these ports into a blocking state. It's basically disabled where it's not forwarding traffic. And at any point, like if I stop getting BPDUs in this interface, let's say that maybe a transceiver failed and the wire's not coming through anymore. The signal's not coming through. So I'm not getting BPDUs here. I go ahead and transition this into an up state, and now we could use it. But so long as things are behaving like they should, that fast link isn't going to get used. Network Guy Dave. Hi, Network Guy Dave. I was just watching your videos on the Cisco Learning Network. Oh, thanks a lot. CCNP score training videos. Good stuff. I'm glad you like that. Thanks for letting me know. That's cool. What I'm doing today is just kind of like a crash course for my local friends, I guess, here in Tampa that are getting ready to go to DEF CON, and maybe some of them aren't, and we're just doing like a workshop on Saturday focused on network security. So this is kind of a prep for DEF CON and a prep for that workshop. But today's defense, so thanks for hopping in, and we'll just talk about defense for a couple hours. And if you got any questions, drop them in. So when we think about spanning tree attacks, what we have here is an attacker, and this could be you or me, running a laptop, generating BPDUs. So we're generating our own bridge protocol data units, and we're sending them to other devices. And here we're saying our priority is 0. Because 0 is lower than that 8192, we would become the root, and all the traffic would flow through us like that. So I described this attack previously in another session. So I think if anyone has attended a session before, this is a second or maybe even third time you've heard this. Should be pretty familiar now. I'm going to keep the story going, but as always, if you've got questions or anything you want to know about, just ask. So again, this is the defense day. So we'll talk more about defense and offense. At least that's my goal. See if I can hit it. What can we do to stop people from screwing up spanning tree? Well, let's slow down a second. What spanning tree does is, we know it stops loops from happening. How does it do it? Well, it takes the port, like when a link first comes up, you plug a cable in and you see like an amber light come on. What it's doing is it's like, wait a second, let me get my bearings straight. And it transitions through different states of blocking, Blocking, listening, learning, then forwarding. We basically want to make sure that we're not part of a loop, that we're not screwing anything up, and then once we're sure, we'll start moving some data around. But if we might be creating a loop or we might be doing something wrong, we don't want to. So we're very slow, we're very cautious to transition from a blocking state to a forwarding state. With traditional spanning tree, this takes up to 50 seconds, which 50 seconds for users today in 2021 is an eternity of time. It's way too long. People have got these M2 drives. I don't know if you've seen them before. They are faster than SSD. They're like PCI Express bus. They just rip. Your OS is booted in 4 seconds. Who wants to boot an operating system in 4 seconds only to have the network take 50 seconds to assign an IP address? Nobody, right? So looking at this describes a feature on this slide called PortFast. As a network administrator, or just somebody who owns a switch, it makes you the network administrator now, you can enable this feature called PortFast, and as it says here, it moves a port directly from blocking to forwarding as soon as the link is operational. So my users, they plug something into the network, boom, they're up and running right away. Sweet, they're happy. The only problem is what happens if you plug in some switches and you make a loop? Well, we're trying to make things happen fast. We skip some security checks there. So a lot of folks like to turn on PortFast because it just makes the network react to changes faster. If somebody boots a computer, turns a link on, in dynamic environments, we can react to it very quickly, which is great. The problem is we could create a loop. So turning on PortFast is nice. It gets things to run faster than normal, but we might want to protect our network. So what we can do is we can enable a feature called BPDU guard. Now these are Cisco slides, but this is universal in networking. Most enterprise switches are going to have a feature very similar to this. They might just call it something a little different. But what we're essentially doing is saying, yeah, go ahead, run PortFast, open up the port, forward frames. However, if you get a spanning tree BPDU, I want you to shut the port down. So we can actually stop those BPDUs from coming into the environment. Where would we do this? We would do this on any link that's not an uplink to another switch or a downlink to another switch. If it's not a switch, it shouldn't be doing spanning tree, it won't be a problem. If an attacker tries to do spanning tree, we can shut the port down. Now when you shut the port down, it could be for like a timer, or it could be indefinite until the administrator comes back and resets it. So like in a college environment where people are more prone to screwing around, maybe I'll have it recover in an hour or 10 minutes. Maybe I don't want to have to look at tickets. In other scenarios, like in an office environment, what you want to do is you want to block it and you want to leave it shut down. This is wise. If somebody plugged in something they weren't supposed to, they bought a switch off of eBay or a garage sale, they decide to bring it into your company, plug it into the wall, it's going to do a BPDU up to the upstream switch. If it's got BPDU guard, it shuts the port down. That user's switch port in their cubicle no longer works. So to get it fixed, they've got to put in a ticket. When they put in a ticket and we go look at the switch port, we see that it's air disabled. Why? BPDU violation. We're going to see that somebody sent a BPDU and they shouldn't have. Now we can go back to the user and go, hey, really strange. It said some unauthorized network equipment was plugged in. And they're like, wasn't me. I don't know where that, look, there's no equipment here. And we're like, yeah, that was weird. It helps create, I call it a healthy sense of paranoia among your users so that they don't plug in crap that doesn't belong on the network. If they plug in something that doesn't belong into the network and it takes it down, you're still probably going to get some of the blame because you're the network administrator. If you don't get blamed, you're still going to have to put out the fire. So just along the lines of like prevention beating cure, BPDU guard stops people from plugging in switches or worse, hijacking our topology. So we can do other things. You can be more granular. You can say, well, it's not a big deal if they plug in a switch. It's not a big deal if they're messing around with Scapy and they're building BPDUs. I'm going to let them do it. But if they try to hijack the root bridge, now I'm going to shut them down. So root guard is a little different than BPDU guard. BPDU guard shuts down on all BPDUs. What root guard is going to do is it's going to look for a scenario where a superior BPDU comes in. What's that mean? Well, every switch knows its bridge ID and it knows the root bridge ID. So if you see another BPDU come along that looks better than the root bridge, that's going to cause a topology change. So with root guard enabled, we tell that switch port, hey, if somebody sends a superior BPDU, shut it down. We look at the port, and it gives us this error called root inconsistent. It's like somebody over there is saying they're the center of the universe. We don't want to believe them. Again, this is a feature that's found in lots of switches. What's it look like to really build all this? Well, from your switch configuration, we see spanning tree PortFast default. With that one single command, if you've got 48 ports, all of them go into the forwarding state immediately. We're like, well, okay, now what? And we go, well, we can go to our trunk links, and or it says here, enables PortFast in all non-trunking interfaces. Now we can go to spanning tree PortFast trunk. If you've got a trunk link and you wanted to enable it there, we could do so as well. If we want to turn on BPDU guard, here you see it here happening from global config. And then if we want to turn on root guard, you see this happening on the interface configuration. And if you don't work with Cisco a lot, what you'd be doing from global config is just say the interface name. So if you've got an interface that you want to mess with, maybe it goes to a problem user, we'd say interface gig 1/4, and the prompt changes. It'll say config -if for interface configuration, and that's where we'd enter that command. Why not just down the ports? Because I still want to pass regular user traffic, but I will shut it down if they try changing the spanning tree topology. So this leaves everything in the forwarding state, and it makes it forward immediately. I'm going to the users and saying, I'm going to make things work fast for you, but if you try to screw with my spanning tree, I'm going to block your port. Good questions. So DHCP we talked quite a bit about yesterday, right? We know that it's a client-server model. Most devices are DHCP clients, and a lot of times that server could be serving more than one VLAN. We looked at DHCP relay yesterday, and we saw how that could occur. DHCP server allocates network addresses and delivers configurations. Can anybody remember some of the things that a DHCP server can tell a client other than just the IP address? And there's a few things. So it gives everybody an option to answer. And there's a delay too. So if you're watching this and you're like, why is he taking so long to do anything? It's because there's just, whenever I ask a question, it's maybe like 10 seconds before I see answers. George has got a good one, the DNS server. That's exciting to us as attackers because I can tell people that I'm the DNS server. And they go, where's updates for my antivirus? And we can shut that off. Amin says DNS, gateway. Good. The gateway and options for TFTP. The TFTP server, that's right. And that's where thin clients and phones are going to get their configs from, and operating systems. Perfect. Yep, gateway. TCP/IP configuration is what DHCP provides. Absolutely. That's what it's there for. Dynamic Host Configuration Protocol. I'll try to define all these as we go through. And there's something else too. There's something called DHCP reservation, which is a good thing to know about. Let's say that we've got a device, and maybe it's just like an old Dell desktop. And I try different things on it. I download different Linux distros. I do weird stuff. It's just my lab machine. But because I'm always changing the operating system, if I wanted to have the same IP address all the time, I'd have to statically configure it. Or, right, because well, let's say it another way. I'd statically configure an IP address on it, but what's challenging is I keep installing different operating systems, Cubes, Parrot, Kali Linux, whatever, FreeBSD. And if I do a DHCP reservation, I can make sure that that lab computer always has the same IP address every single time. Even when you delete the operating system, do whatever, when you reboot it and it comes back with that same MAC address and it does a DHCP request, I tell my DHCP server, anytime you see that MAC, always give it this IP. Why would you do that? You could create an access control list. Again, we're thinking your home environment or your lab at work. If you've got different devices that you want to have basically controlled differently through ACLs, we can say, my lab computer always gets this IP address. Why? Because I stored a DHCP reservation mapping its MAC to an IP. Okay, great. Whenever I boot, whatever OS, it always gets the same IP. Why is it fun? Because on my access list, I can restrict a bunch of things that I don't want that computer to do. And no matter what the operating system is, I'll always get the same permits and denies on an upstream interface, which is pretty neat. Oh, Network Guy Dave pointed out your subnet mask as well. Good one. And that was what we were saying. I've been trying to drive that home all week, is that your IP address is great, but without the subnet mask, it doesn't mean anything. Good catch. The DHCP process, you do something called a discover, which is like you shouting. You're like, hey, I need some IP addressing information. Remember, none of this is authenticated, and everybody hears it. So it's out of the clouds, out of the forest, maybe from a bush or a trash can. Somebody's like, psst, hey, you want some IP addresses? That's the offer. We don't know who that's really coming from, but based on that offer, we do a request. You go, you know what? I would like some IP addresses. And they go, okay, fantastic, here you go. It's 4 steps. We discover the server, they give us an offer, we do a formal request, formal acknowledgement. At that point, the IP address is now leased to us. The server will maintain how long that lease is for, and then at the end of the lease, we'll either change our IP address or we can request to keep the same one. So, server spoofing. We talked about this a little bit before. You can turn on a DHCP process on any computer that you want. And that can be really problematic because anyone around you that broadcasts, you have the ability to offer. So if you're giving them bad information, it's going to screw things up all over the network, whether that was your intent or not. So how does it work? Client sends a discover broadcast address. The attacker gives it an offer. He's like, psst, I've got some IP addresses over here. Because we don't have authentication on any of this, we're like, I don't know, looks good to me. We accept the illegitimate address as a DHCP request. Then we go, the attacker will respond with an acknowledgement. And at this point, a couple things happen. Like in their storyline, they say the legitimate DHCP server sends out an offer that was too late. Maybe, how do I know as an attacker that I'm gonna beat the DHCP server? Being closer to the victim, like in the same subnet, is like a pretty good approach, I suppose. But a better one is to drain the DHCP server. Remember we said it's a pool of addresses? So we drain the pool. And we do that by just sending a lot of fake requests, one after another, until there's no available IP addresses. At that point, your DHCP server is DOSed. What fun is that? Nobody can get on the network, nothing works. That's not our goal. We want man in the middle. So we get man in the middle by becoming a server. So when I talked about draining the pool, this is referred to as DHCP starvation. There's different utilities that'll allow you to do this. Yersinia has got a lot of capabilities built in. This is one of them. There's other tools out there that'll just go ahead and suck all the IP addresses off of it, like Gobbler is always one that comes to mind. Its only point in life, it's just a dedicated tool just for draining DHCP servers. So we'll create a spoof MAC address, we'll make a request, we'll go ahead and fill out the offer, acquire the IP, hang on to it for 12 hours. As soon as we're done, we just do another, one after another, until the server's unable to assign any more IP addresses. So that's a starvation attack. The point of starvation is so that our offers are not competing with the DHCP server. I don't want the legitimate DHCP server to try to have a moment to get that offer in. So what can we do against this, to defend against it as network administrators, as good guys? Well, there's a feature on switches. Dell has it, Cisco has it, HP has it, called DHCP snooping. And it really does two things that are very cool. Basically, we turn this on a VLAN by VLAN basis. What's cool about that is when you're working with security functions, a lot of times security can break things. Sometimes it's just the security control being wacky. Sometimes it's us implementing it incorrectly. So the cool thing about DHCP snooping is that it's turned on a VLAN by VLAN basis. You can create a new VLAN just to test it. Put some old laptops in there, see how it works. If you feel good about it, roll it out to another VLAN that's production. In that one VLAN, deploy it, monitor it, make sure you like it. Then we can go from network to network to network, enabling it where it's needed. Really pretty cool. With DHCP snooping, we turn it on for a VLAN, and your job as the admin is to designate which port is trusted or untrusted. All ports are untrusted by default, which means all ports in that VLAN can only forward a DHCP request, but they can't forward the acknowledgments. They can't make the offers. So basically, anybody who's untrusted can request, but they can't tell anybody what IP addressing to use. It's easy because most devices are clients. What we have to do is go to the few interfaces that actually have DHCP offers. So I'll show you. Notice the server at the bottom says legit DHCP server. So that port would be trusted. Now, when you look at the links between switches, these ports should also be trusted because there's a good reason that a DHCP request would go through there. Let's say that this switch, I'll get a highlighter so it's bigger. Make that red. There. So let's say that this switch right here had to be rebooted for a software update. When that happens, spanning tree is going to do a topology change, and our traffic is going to flow like this now. We have to make sure that when there's topology changes and we're forwarding traffic over alternate links, that those alternate links are also trusted. So think about any link that a legitimate offer could possibly come through, make sure you flag it as trusted. If you don't, if there's a topology change, people may not be able to pull IP addressing. They're going to wonder why, they're going to scratch their heads, they're going to complain, and then all of a sudden it'll just work, and nobody will know why, because your original path was restored. So the one thing that it does, put that up here, is the trusted versus untrusted ports. Has everybody got that? The second thing that it does, and this is going to play into another feature called dynamic ARP inspection, DHCP snooping enables a switch to build a table that maps client MAC addresses, IP addresses, VLAN, and port ID. How cool is that? So what I'm saying here is that our switch wasn't previously paying any attention to DHCP. Now we're like, hey switch, let DHCP over here, but don't let it in over here. Well, the switch is like, man, if I've got to pay attention to what's happening with DHCP, I might as well look inside each of those messages and start building a table of what MAC addresses and which IP addresses are actually authentic. Because it's got this idea of trusted versus untrusted, it can monitor traffic going through the trusted interface, determine which MAC address to IP address assignments are valid, and then record that in a table called a DHCP snooping binding table. Once we have that table, we can later analyze ARP traffic, and whenever somebody sends a gratuitous ARP or any ARP reply, and it says this IP goes with this MAC address, we can go, wait a second, let me check my list. And if it looks good, we let it through. If it doesn't look good, we don't let it through. So this is really pretty cool. This table, once again, will be leveraged for dynamic ARP inspection. Let's see, Raymond's got a question. He says, can an attacker determine what is the trusted port and do a DOS on that as well, or not possible? I don't want to say that anything's not possible, but there's not an easy way to do that I know of. You know, you'll hear a DHCP request, you'll send an offer, and if the offer doesn't go anywhere, meaning if it doesn't escalate into, you know, basically the user checking out that IP address, we know that something's happening. We could guess that it's trusted, but you can't really be certain without looking at the switch. And would DOS be a possibility? Sure, because you could DOS through like malformed CDP frames. A lot of times when an attacker can't pull off a sophisticated attack because you have controls, they're like, oh man, just screw it, we'll burn this place to the ground. And they'll try to do DOS. They can't get man in the middle, they can't get your database, but they can still just be obnoxious. So I guess DOS is always a possibility. So here we've just got an overview of ARP, in case anybody wasn't here the last 2 days. ARP is Address Resolution Protocol, and we all do it all the time. Anytime I'm moving from layer 3, which is IP, to layer 2, I need to determine what that layer 2 MAC address is. Oh man, why did it do that to me? So what is the layer 2 MAC? And ARP is the process responsible for this. Remember that this is a broadcast. So every time you ARP, everybody else in the network hears you doing that ARP. They know who you're talking to because you had to make a request to resolve this. So ARP cache poisoning works like this. Whenever somebody does an ARP request, they get an ARP reply, they store it in their ARP table. However, if somebody's malicious and they just start sending out ARP replies that you never asked for, your computer will accept it and store that information anyhow. It's gratuitous ARP. One of the easiest man-in-the-middle attacks in the universe, still works really well because some first-hop gateway protocols leverage the same mechanism. So vendors are slow to shut it off. But we can prevent it, as I'll show you here. With dynamic ARP inspection, we can stop those gratuitous ARPs. This is our countermeasure. What do? Well, we take dynamic ARP inspection and we associate it with either a trusted or untrusted state. Trusted interface bypasses dynamic ARP inspection. Untrusted interface undergoes dynamic ARP inspection. So anything that's untrusted, we're going to look at what your ARP behavior is. If it's not valid, we'll throw it away. Now, let's talk about what's valid for a second. If I think about, and my sinuses are jacked up, I'm sorry, but if I'm thinking about doing a network attack and I'm going to do ARP poisoning, most of the targets that come to my mind have static IP addresses. They don't have dynamic addresses. So if it doesn't have a dynamic address, how would dynamic ARP inspection ever know what the entry should be? Remember, this process called dynamic ARP inspection is leveraging that DHCP snooping binding table. Go, well, my router, my printer, my domain controller, my logging server, my CA server, all these devices have static IPs. So it wouldn't know it from dynamic observation. Well, as the administrator, you can create something called a static ARP ACL. It sounds scarier than it is. It's just a text file, basically, that's got IP address to MAC address mappings. So you say, hey, switch, my router is this IP, it's this MAC address. Once that static entry has been told to the switch, anybody who ARP poisons, that ARP poison will be denied and a log will be generated. So A, it won't work, and B, if you're reading your log files, you'll know that somebody's in your network trying to do ARP poisoning. Pretty cool. It's one of the oldest attacks, it's an easy attack, but what's cool is that it can be easily mitigated. The problem, a lot of people don't do it. So it's just a matter of getting into your equipment, seeing if it has features that support this. And remember, we're turning it on a VLAN by VLAN basis. So it's not like you've got to fix 75,000 network ports all in the same day. We can start on individual networks, individual ports, and just secure the network one port at a time. So what's it look like if we've got dynamic ARP inspection enabled and somebody tries poisoning? Well, over here we've got the attacker saying, I'm the gateway 10011. Here's my MAC address. Well, when that comes in, it gets evaluated. Historically, it never was. But now we look at it and we're like, wait a minute, that isn't accurate compared to the binding table, and then we can go ahead and drop it. So that particular frame is never going to make it beyond the switch. These are pretty old capabilities. I'd say 10, 15 years old, 10, 15 years maybe they've been around, and on all the different vendor switches. So some of this will be familiar from yesterday because we talked about firewalls a little bit. Some of it will be like a helpful repeat, I hope. So when we look at a firewall, it very often has three interfaces. We've got inside, we've got outside, and then we've got DMZ. The demilitarized zone is less trusted, less protected than the inside, but it's still more trusted and more protected than the outside. The outside, the internet we know is hostile and evil. So the DMZ gives us a safe place-ish to basically put some servers that are going to have, be accessed from the internet. And we say if it's compromised, at least there's this barrier preventing it from talking to all the other computers on the inside. Yesterday with our discussion of VLANs, we talked about how we could take this kind of standard, what I call a three-legged firewall approach to firewalls, and we could make it multi-legged. Could be a spider, for instance. We were saying that what happens if in the DMZ somebody gets compromised and starts hitting other hosts in the DMZ? Well, we can use VLANs, we can trunk to the firewall, and then we can make all the host-to-host traffic within the DMZ get routed through the firewall through the use of VLANs. Really pretty slick. We talked about router on a stick. That's a firewall on a stick. You're doing your layer 2 switching on a switch, and then to get between the VLANs, that would all happen on a firewall. So again, this is 3 networks, but it could just as easily be a whole lot more through the use of VLANs in the DMZ. Or if you had different internal networks that you wanted to route through a firewall. Amin says, what if we have ESXi with one interface and multiple VMs? Can we use dynamic ARP inspection for multiple ARP bindings on the same port? Sure. Yeah, so long as it knows that all those valid hosts are on that one port, great. So when we look at firewalls, we basically have got different capabilities. We used the term yesterday, packet filtering. And that's where I said a switch can sometimes be a firewall. Isn't that weird? Switches are better at routing than routers are because they can move more packets. And then it can also be a better firewall. Not necessarily better, but we call it a layer 3 switch if it routes. But even a layer 3 switch can do layer 4 filtering. And the reason I say it like that is because we can put access control lists on individual interfaces, on routed interfaces, we can apply it to an entire VLAN. But these access control lists are basically permitting or denying traffic sourced and then destined either from Ethernet or IP addresses or port numbers. So whether it's layer 2, layer 3, or layer 4, an access control list can perform filtering on different traffic flows. So a switch can be a layer 4 firewall in the sense that it's doing packet filtering. What we tend to think of is dedicated firewall appliances. We think ASAs, we think FortiGate, we think Palo Alto and Checkpoint. Those are of course going to be stateful packet inspection firewalls with deep packet inspection, and today we even call it next generation firewall because the deep packet inspection has got so many granular tools that we can block very specific things, such as like Facebook chat, but not Facebook Marketplace. And we could block Facebook games, but maybe not Facebook Messenger. So when you look at a firewall, look at the requirements of a firewall. Must be resistant to attacks. This is probably the thing that I get most excited about. How cool is it to be able to hack a firewall, to make a firewall crash? You're like, wait, this is the one thing that's supposed to stop hacking from spreading from point to point. Wouldn't it be neat if you could attack it? So that's, I think, kind of like the holy grail of hacking. It must be the only transit point between two networks. So what happens if I've got a firewall that connects this network and this network, and then I've also got a server that's multi-homed? We say a server is multi-homed if he's got 2 NICs. Or she. Your server could be a girl. So here's my server. And we say this is a bad design. The firewall is supposed to stop the spread of fire. It's supposed to evaluate everything that goes through. By having the server here, packets could come in and out of the network without there being any communication through the firewall, meaning we've got no idea what's happening. So just to kind of stress that, your firewall should be the only transit point between different network zones. Your configuration will be based on your company's architecture and policy. That all makes sense. When we talk about packet filters, we're filtering on a packet-by-packet basis. It's rules of permits and denies. We filter based on IP address, protocol, and port number. We can filter on the source or the destination. This is what an access list looks like. So if you haven't seen one before, I apologize. I've used the word 100 times now. When we say access list, it'll have a number. This number matters. You've got different numbers for different types of ACLs, but 100 is extended. And extended ACLs include a source, which is any, and it has a destination. And the way that it reads is we say access list 100 permit TCP traffic from anywhere destined to 10.10.10.10 if it equals www. Well, that's an alias for port 80. Then what happens? We say we'll also allow traffic if it's destined to the same host on 443. And you'll notice we did the same type of rule for .11, 80 and 443. And then for .12, this is our FTP server, excuse me, we're allowing FTP and FTP data. So 21 and port 20. At the bottom of every access list is something called an implicit deny. Does anybody remember that term? Implicit deny was saying, hey, if I don't have a rule for it, drop it. So anything that doesn't have an entry will be thrown away. That's what access lists do. What they did here a little bit differently, and I'll use a highlighter, is that they use this keyword called log at the end. The deny IP any is implied. It's already there. It's just the way that access lists work. But the fact that we use the keyword log there, and you could have put the keyword log on any of these other entries, it says whenever a packet comes in and matches this, I want to generate a syslog notification. So the router, acting as a firewall, is going to send a message off, UDP 514. This is where syslog's listening. And we're saying, hey, somebody just tried to do something that's not in our list. And this is a very basic indication of compromise. This is somebody who's misbehaving. We can go investigate it further. So those logs aren't generated by default, but we can basically tell it to be. Now the next step up after a packet filter is a stateful firewall. Why is it stateful? Well, it controls access on a session-by-session basis, and it does that through the creation of something called a state table. So a packet filter just sent the packet and it didn't care. Let me show you that in a little more detail. So if I've got a router here, router has an access control list, and it says only allow 80, only allow 443, and the web server's back here behind that router. When I send a packet in, and then packets are layer 3, segments are layer 4. So there's my packet, there's my segment. My segment is destined for port 443, but the flag is set to fin, which is to finish the communication session, and then reset, which says tear down your TCP session. Now that's really weird because there is no TCP session. So what somebody's doing is they're spoofing these TCP flags and they're sending them to the web server. Now, if it's a packet filter, it lets that go through. If it's stateful, it will see a fin reset and it'll say no way. It says the first packet of every flow needs to be a SYN, followed by a SYN ACK, followed by an ACK. That's the three-way handshake that we have to get our sequence numbers in check. So stateful firewall says I must see that or the packet never goes through. When we do ACLs on switches, they're not stateful. So it's not thinking in this detail. All it's doing is looking at the port number and saying it looks good to me. So was it, let's see, Raymond was asking earlier, said can attackers determine what's going on with trusted ports? Can you do denial of service? Kind of building on Raymond's mindset there. When we look at this with stateful firewalls versus packet filters, as an attacker, I can tell which one you're running, right? So I'm going to figure out what's open with a three-way handshake. I go, haha, look, port 80 is there. There's a web page. I go, what happens if I send like an ACK fin to that port? If I just send an acknowledgement to that port with a wacky sequence number, what happens? And if I get a reset back, it means that that packet made it through to the web server, and the web server said, I'm not talking to you, I don't know what that is, and it tried to tear down the session. Cool. If it was stateful packet inspection, and I send like a fin ACK, or even just an ACK to that port, I know the port's open because I did a three-way handshake, but I come back and I try just to send an ACK, and it gets silently dropped. I go, ooh, they don't have a packet filter, they have stateful packet inspection, which means it's a generation above being a packet filter, and it could be all the way up to next generation firewall because all of those things do stateful packet inspection. Pretty cool, right? We can determine what somebody's perimeter defenses are by just throwing weird packets at it. Do a full TCP connect scan with Nmap first, but then you've got things like fin scans and ACK scans. Those are useful for determining how intelligent this filtering device is. A simple packet filter doesn't look at the flags, so it just lets them slide by. So looking at stateful firewalls and the concept of deep packet inspection, this is a real good concept. This may be a little bit hard for some of you if you're not, if you haven't spent a lot of time with firewalls, but if you can wrap your mind around this one concept, it will serve you well for many years to come. So first off, we're going to learn how FTP works. With FTP, there's two modes, active mode and passive. What makes FTP so funny is that it uses two different ports. It uses a control port and it uses a data port. So the control port is where we actually log in and we ask for files, and the data port is where the file transfer actually occurs. So that's a little weird. We're like, all right, we've got two different sessions. I'm like, well, wait, it gets weirder. Whenever a client talks to a server, the client initiates the connection, does a TCP three-way handshake, logs in, and then makes a request on port 21. It's like, hey, server, can you give me some files? Now watch this. This is where it gets so weird. The server creates that second session. It initiates with the TCP SYN onto some new port number. Super weird. Let's take a look at how a firewall normally works. When we look at a firewall, you've got an inside and an outside. In and out. And we say traffic is allowed to go to the outside, but from the outside, it's not allowed to go in. It's not trusted. Now, what makes this easy, and with stateful packet inspection, we look at packets when they go out. So this packet flow up top is being evaluated by that firewall. And it looks at the source and destination IP, source destination port numbers, and it takes that state table and it creates an entry for the return traffic. In other words, there's a force field here, and we go, oh, I just saw a TCP SYN go out to host B over there, and I poke a hole here, and I go, I bet I'm going to see return traffic with these sequence numbers any minute. That's what stateful packet inspection does. Now, what deep packet inspection does is it takes this and it builds upon it. It sees that there's a connection going out from port 21, and the firewall is smart enough to know, oh, 21 is FTP, and FTP is a little bit crazy. That's what I was showing you here with this active mode. You see, when a client talks to the server, the client's initiating the connection there from right to left. What the client is saying on this control port is it's going, hey, I want you to connect to me on port 2010. So this client opened up a TCP socket on 2010 and it's listening. It told that server to come connect to it on that port dynamically. What it's not thinking about is that there's a firewall here in the middle blocking inbound traffic. So what deep packet inspection does is it says, hey, when you see something on port 21, remember this is a segment, this is like an envelope, source and destination port. We go, if you see a destination port 21, open up that envelope and look at the message inside. That message inside is going to have FTP methods, which are kind of like a verb. When I see somebody saying port 2010, I know they're listening on port 2010 for an incoming connection. So the firewall, by evaluating this payload, that's why we call it deep packet inspection, it knows it can come over here in this firewall rule set and go, I'm going to poke a hole in my external perimeter to allow the new flow to come in. And that's what they're showing you on that bottom blue line here, where it says dynamic data connection. This is a session being launched from port 20 towards that server on 2010. This is so weird because it's a different port number. If you're not doing inspection of FTP traffic, this wouldn't work. What your firewall is basically doing is it's eavesdropping on the communication of two other parties that don't really know the firewall's there. They're not thinking about it. And when it's eavesdropping, it's like, oh, wait a minute, you want to do what? And it'll fix the firewall table to allow those flows to automatically go through. Pretty cool. And while it's going through, it's evaluating them. It's making sure the first message of a TCP flow is a SYN. It's making sure the sequence numbers make sense. It makes sure that if somebody tries to tear a connection down, they send a fin to tear the connection down. If the firewall sees that, the other side should be sending a reset. and it's like, hey, I don't see a reset coming in. And if it doesn't, the firewall goes, screw it, I'm going to spoof like I'm either party, and I'll do resets myself. So the firewall kind of gets involved and takes very granular control of the sessions that go through it. Some firewalls are called a proxy server, if you've ever heard that term. All a proxy server means is that your TCP connection is being built and established to that system. And then that system is responsible for building a whole new connection out. And there's intelligence that runs on that software that's responsible for brokering each of these connections. Because you're in the middle, you have full accessibility to all of the payload information that goes through. So anytime you hear people talking about SSL decrypt, has anybody heard that at work? SSL decrypt means that we're going to make our firewall broker connections. You're going to do a TCP three-way handshake. You're going to do digital certificates, X.509. You're going to talk and build an encrypted session. But your encrypted session goes to this intermediate server. That intermediate server can see inside of all of your data, and now it can do things like data loss prevention. So DLP is happening here. Intrusion prevention is happening here. Why? Because we can see inside of everything. When you do SSL decrypt, this is effectively what you're doing. And I'm not going to go through all the slides, but we'll go through a bunch of them. So next generation firewall is just taking this and building it a bit more. Cool, right on. Amin says uses it for IPS. Right, because if you're not inspecting SSL, just like we use encryption to keep our data safe from hackers, hackers will use encryption to keep their adventures safe from pesky system administrators. So encryption's really a dual-edged sword. Having the ability to decrypt all the traffic that's going through your firewall means things shouldn't be sneaking out undetected. So a next generation firewall just kind of builds. It says, and who knows what they're going to call them next generation. We're already saying next generation firewall, kind of cynically, but in reality, not sure what the next title will be. They're doing a lot of the things we've always done. We've had URL filtering for many, many years. It used to just happen on a third-party device. Like we would forward URL requests to a sensing server, or filtering server like WebSense, and then we would just basically deal with the reply. Now what we've seen is the firewall administrators are offering the URL filtering as a service that they control, and then they charge you for it annually. This is a good term to know, application visibility and control. When people say next generation firewall, this is what they mean. And this is basically a glorified or sophisticated version of deep packet inspection. It means I'm going to look into the application and I'm going to manipulate what people do. Like I'm going to allow some controls, but not all controls. Just granular awareness of the application. So a context in the world of Cisco is a virtual firewall. FortiGate calls it a VDOM. Lots of vendors do this. We can just create different virtual firewalls and give different administrators the ability to create their own rule sets. IPS means that we're getting a signature set from our vendor probably every couple days. And it just has definitions of what known attacks look like. So if anybody tries to use an attack we know about, we've got a signature match and we can drop it. Advanced malware protection is basically Cisco's antivirus. And identity-based access is really kind of a clever idea. A lot of vendors do this. Here's my firewall, and my firewall is going to have rules in it. And those rules are very often built with access control lists. Access control lists are typically built on IP addresses, but nowadays we've got the ability to do usernames. And this is pretty cool. I'll say access list allow Raymond to get to the Exchange server. And the way that that works is a firewall talks to an Active Directory connector, which talks to Active Directory and reads the security logs. The way that Cisco builds this, you use WMI, I think it's Windows Management Instrumentation or Windows Management Interface. It's a mechanism to talk to Windows servers. It's going to allow us to parse through the security log, and the security log is going to tell us that Raymond just logged in at 10/1/1/13. Sweet. So that's retrieved through WMI. It's stored in this. This is just basically a virtual machine, but it returns those details as a radius AV pair attribute value. So it says Raymond equals 10/1/1/3. So now inside my access list where I had Raymond's username, I can use 10/1/1/3 there, or 13. I just had to resolve it from an external server. So kind of cool. They call that identity-based network services. So how about logging? Your logs can generate tons and tons of data, and if it's too much data, is anybody ever going to look through it? If you're logging to something like Splunk, Splunk is free, right? Kind of. If we create less than 500 megs a day of logging. So instead of logging everything, why don't we just log things that are really important? Specifically, anything that's coming from the firewall, because it's a security device at your perimeter, it's something that should be monitored. So we want to be able to recognize network attacks. It's useful for performing forensics. And of course, it helps us comply with regulatory standards. The whole idea of centralized logging is that it should be, they just say centralized logging servers should be provisioned and maintenance plans put in place. But realistically, I found that you'll have many different logging servers. You could have syslog over here being used by the network team. You could have Splunk that's being used by your SOC. You could have a server admin team. They're using SolarWinds. Even though there was a new attack a couple days ago. And you're like, how do you get this one device, like a router, to go to those 3 destinations? They sell syslog repeaters, which is just a virtual machine, but you point your logs to the repeater, and the repeater lets you fill multiple servers. So that's pretty cool. It takes the load off of creating 3 messages off that router. Sometimes logging, just creating it and sending it can be burdensome. So we take that burden and we give it to another device, a repeater. And then the repeater can send it to multiple syslog servers for multiple departments. This can be cool because a lot of times, if you're a real sophisticated attacker, maybe you try to take down their logging server. Well, if they've got 3 different logging servers, good luck. So we don't have to talk about the products so much, but what is good to know is that there's a concept called a virtual firewall. And all the vendors are making these now. Checkpoint, Fortinet, Cisco, whatnot. And what you do is you deploy your hypervisor. This would be like VMware ESXi that Amin was asking about. And what's coming into the ESXi? Well, we've got network connections, and these are trunk links. We're carrying all these VLANs through tags. But once you get into the server, it's got what's called a virtual switch, or vSwitch. That virtual switch can be hooked to virtual ASAs, and now we can actually do firewall services on the box. What's so cool about this is previously, if you had 2 different, like let's say this is my web front end, and this was SQL, if I wanted to pass it through a firewall, I had to come off of this physical server over to a data center switch, many times only layer 2, take that up to a top of rack switch, take that across the data center to where my firewall is, firewall makes a forwarding decision, and then sends each packet all the way back. How ridiculous is that? It's going to cross all that fiber, all those data cabinets, when it was really just 2 virtual machines, 2 different chunks of memory trying to talk on the same computer. Silly, right? So we can use virtual ASAs on a single firewall, or I'm sorry, on a single server, so that the virtual machines on that server are still separated, but we don't have to take the traffic off the server to do these types of filtering. Pretty groovy. So when you deploy firewalls, this is really a cool concept, especially for anybody trying to harden your house or your lab. If you're working from home and you want to keep your customer data a little bit safer, you can get a lower end firewall and just separate yourself from the rest of your house. And when you do it, you can deploy it in 2 different modes. Routed mode is what most people have by default, and that's like a normal firewall sitting between 2 networks, like the ISP and you. And then you've got what's called transparent mode. Transparent mode is also known as stealth mode, and this can be super, super handy. I had a scenario at a hospital where they had an MRI scanner, and it was probably $1 million or something, very expensive. They had software over here that was used to operate the MRI scanner and display the images. The software that they used was pretty old, and it was proprietary. The company that made it went out of business. And whenever they applied a service pack or a software update to this particular system, it would break the proprietary software, and there wasn't a good way to fix it. So they said, well, we've got to take this system and we've got to keep it running, and we can't patch it. I said, that's not a real solution. It's vulnerable. It's part of your network. What are we going to do? And this system worked with a bunch of other systems down here on a common subnet, and the scenario was such that I couldn't change the IP addressing. What I was able to do was put a firewall here in transparent mode. So let's look at what that means. It means that if this host is 10.1.1.15, and these hosts are 10.1.1.4, 5, 7, 9, they're all in a /24 space. Everyone's in the same subnet, except what's so cool is that I've got a firewall between them. My firewall in transparent mode is working at layer 2. They call it a bump in the wire. It's not a normal hop. This isn't anybody's gateway. Traffic flows through it. So what's so cool is you can stealthily inject this into an existing environment, not change any of the IP addresses on any of the devices, but you still get next generation firewall functionality. We can dig into the packets, we can pull them apart, we can look at the payload, we can do IPS, we can do detailed IP accounting. What's so cool about this is this was an older system that I can't patch. Well, the attack that you would use to break into it was also old, which means there's an IDS signature. So when I run IDS or IPS on my next generation firewall, I can drop the attacks that were destined for this server, so the server can keep running that MRI. This was not a pretty solution. It's not something I wanted to do, but it's something that you could do, and it could kind of save the day, just by deploying a firewall in a different mode where it doesn't alter the network topology. So I don't know that you'll run out and use that tomorrow, but just to understand that a firewall can operate in that mode, I think could be pretty handy for you. Looking at single versus multi-context, I might have a slide for that as well. Yeah, right here. Kind of a funny slide. Let's say that you have one firewall. You can create virtual firewalls with it. Here's virtual firewall A, B, and C. So what's so neat about that is, let's say that somebody else runs a different department than I do. I'm a manager, they're a manager, and they're very strict. They say, my users can't look at anything on the internet, they can't go to these sites, they can't mess around, they're here to work. I go, okay, that sounds like a good thing. And I talk to my guys and they go, we're here day and night, we're here all the time, we've got these long hours, sometimes we want to look things up, your firewall keeps blocking us. I go, okay, I think things should be loose. I can disagree with the other firewall administrator, but we can both have separate rule sets for separate users, or as you see here, separate customers, and we're doing also in the same physical hardware, which is pretty slick. Alternatively, if you've ever thought about like leasing real estate, say you want to be a landlord, you could basically buy a firewall in a co-location facility, you create virtual firewalls, and you lease these virtual firewalls to your customers. Your customers have got websites, FTP servers, mail servers, infrastructure. Did they bring a firewall? If not, you could just lease them per month virtual firewall that actually runs on your physical box. So Cisco typically tops out at around 50 virtual firewalls per server. But what gets so cool about this is if I had 50 physical firewalls, and this is how we've done things in the past, if I had 50 departments, like I saw this at University of Wisconsin, I don't want to say it was 50 departments, maybe it was like 36, but all of those departments had a firewall, and all their firewalls were redundant. So 36 departments equals 72 firewalls, equals 72 power cords, equals a lot of fans and heat and wires and crap. By doing this in software on faster boxes, we're still able to achieve high availability, but we do so with 2 firewalls. If I had 50 virtual firewalls, I'd run 25 on the top and 25 on the bottom. If either one fails, the other one can take over. So with 2 physical boxes, very powerful boxes, I've now eliminated the need for tons and tons of rack space, tons of power cables, tons of UPSs. It just made my data center a lot more streamlined. It's pretty cool. So with our firewalls, we typically want to have failover capabilities. So we have a dedicated link between them, and your hello messages and your state table replicated across this. Talked about this a little bit yesterday. If anybody was here yesterday, we said VRRP, HSRP, and GLBP are what routers use, but a lot of times a firewall will have a dedicated interface with a dedicated cable just to handle state table replication and failover processes. If you're using multi-context mode, and that means you're basically using virtual firewalls, what you can do is have virtual firewalls, like 25 of them run in there, 25 of them run in here, and then replicate the state table back and forth. Both firewalls are active, they're passing traffic, but should one fail, all the traffic will move over to the other one. So that's the concept of active-active. Clustering just means that we're grouping multiple ASAs together and then doing load distribution across all of them. I don't need to get into all the ASA commands. Let me get back to our agenda. So, want to talk about secure management, firewall essentials, DNS, PKI. Does anybody have any questions on firewalls? I feel like that was just the very, very basics of it, but I also felt like that's stuff we all should probably know. I don't see any questions coming in, so I will kind of pivot here, but if a question does come in, we can dive back into firewalls. So let's do DNS real quick, and then we'll get into PKI. I think you know DNS already. DNS is a query to UDP 53, and then it's a response. This is in clear text, and it's not TCP based. So this is something that can be spoofed pretty easily, and it can be modified. What makes it worse is a lot of times you've got a workstation. The workstation will do a DNS lookup, and the DNS lookup just goes to maybe your firewall. So for example, my Frontier firewall through DHCP tells all of my internal clients that it is the DNS server. Well, what's happening is it's doing DNS lookups to the service provider, and it wants to make sure the service provider can log everything. That's clean and easy. The other way service providers do it is just by capturing your data. So whenever you do DNS traffic, they can tell an awful lot about you. What websites do you shop at? How often do you shop there? What websites do you go to first? And they can kind of build this persona around your web browsing habits. They do this by mining your DNS traffic, and then it gets sold to third parties, which is kind of creepy. They have a really good idea of who you are because you're the customer. They're billing you. They know exactly who you are. So the fact that they can guarantee who you are with all of your web traffic, it makes that a pretty valuable thing to sell. And I think it's a little bit gross. Your ISP should be in the service provider business, not the spying business or advertising business. But this is what they do. ISPs are no good. And then you could get into nation states and hackers and everything else after that. But we really want to consider the sensitivity of that DNS traffic. So much of hacking methodology is about scanning and OS intelligence perhaps, and probing and figuring things out. Well, I think it's cool to learn as much as you can without doing the probing. So here with DNS, if I've got the ability to do man-in-the-middle attack, we could do that with spanning tree manipulation or ARP poisoning. When those messages come through, I can now evaluate them. I'm going to see everybody's DNS. If I can see everybody's DNS, well, I can learn an awful lot. I know what operating system they're running. I know what office management software, like are you running Google Docs or are you running Microsoft Windows? Are you using Foxit PDF Viewer, for example? It's a nice third-party PDF viewer. If you launch Foxit, the first thing that happens is it checks for an update. When it checks for an update, that's through DNS. So when you launch VLC, it's going to check for an update. If you launch Notepad++, it checks for an update. You can imagine so many applications, as well as your antivirus or endpoint protection. So as all those devices are beaconing and calling home, they do so by doing a DNS lookup first. If I can monitor DNS, I can learn an awful lot about the target organization without sending out any scans. So it would be real good if your DNS traffic was protected. There's two different methods that we can take. And they're a little bit different. So DNSSEC is really about authentication. If you want to make sure that the answer is coming from a trusted source, use DNSSEC. Does that stop people from spying on you? No. It stops people from lying to you and sending you to the wrong destination. When we look at DNSCrypt, this is privacy. This is encryption. This is AES. This stops a service provider or attacker or anybody else from looking at what it is that you look up. So these are things I think that everybody should use. Now the problem is you would have to go around and configure this on every single one of your endpoints. And you're like, well, wait a minute, I got to go to my Nintendo Switch, I've got to go to that printer, I've got to go to that thermostat, and I've got to configure all this. I don't think there's a DNSSEC implementation for my Nest thermostat, right? Like, what do you do? So what we can do is start here. Let's say this is our DHCP server. DHCP server makes an offer, and it tells every client dynamically who their DNS server is. Well, that's pretty cool. Once they know who the DNS server is, let's say that this is Alice. Let's put an A there. Alice is going to do her lookups to whatever DNS server we tell her. Well, just using something like a Pi-hole. Pi-hole will support DNSSEC and DNSCrypt. So if I can get that one user dynamically to use my internal DNS server, I tell my internal DNS server to use DNSSEC and DNSCrypt. Cool, right? So now I've got one system that has to be configured for this, and I point all of my other systems to that one box. On my perimeter firewall, I say this DNS server is allowed to do DNS lookups. No one else is. So if somebody goes in their computer, they type 4222 or 8888, it's going to get dropped at the firewall. The only thing you're allowed to do is send traffic to the internal DNS server, who's now going to protect everything when it goes out. I only had to set DNSSEC and DNSCrypt up one time. Now internally, is my DNS traffic still susceptible to attack? Yes. How would I prevent that? Setting up DNSSEC, DNSCrypt on every single endpoint. I don't know that that's appropriate for your threat model. So a lot of times clear text DNS internally to a central server that encrypts it will take you a long way. So just some recommendations for defending your DNS. Public key infrastructure, or PKI, is the process of using public keys in the format of digital certificates through a certificate authority. Let's break that down a little bit. So I said public keys. If I want to do SSH to manage this server over here, one of the prerequisites is go out and create some RSA public keys. And it's really a public key which is shared with the world and a private key which is kept secret. That public key, when we use it with SSH, is just sent across the wire. It goes, hey, here's my public key. It's not in any pretty format. When we use SSL, better yet, call it TLS, what's happening is this public key, just like before, is going to be presented in x.509v3. We talked about this a little before, but we'll just see it again. The central authority is typically a trusted third party between two different businesses. So if I'm going to peer with some other company that I met at a conference, we're going to build a VPN. The best way to build the VPN is with digital certificates. A less secure but easy way is with passwords. So because we're a security shop and because they're security conscious, we say let's go ahead and let's get enrolled with the centralized CA server. It could be Let's Encrypt. It could be Entrust. It could be VeriSign. What's important is that you both agree on who the middle one is. Who is the trusted third party? We both have to trust it. If we say the trusted third party is Entrust, what we do is we take our public key and we send it to that CA server. Remember this? This is the certificate signing request. And it contains the public key. And it contains the identity. And it contains the CA server. I'm sorry, the certificate signing request just contains the public key and your identity. Once the CA server sees that and authorizes it, says, yep, those two go together, they return your x.509v3 digital certificate. And that's what's actually used in TLS. That certificate is what I was talking about when I said it's your public key, it's your identity, it's the CA server, and its certificate details. So for those two devices to communicate with TLS and authenticate each other, each one needs a public key. It needs to send that public key to a CA server with identity information. It could be your fully qualified domain name, might be an email address, just something meaningful to tie the big ugly public key to. CA server will see that, the admin will, they'll verify it, and they'll go, okay, cool. You get a certificate. And again, it's the public key, it's the identity, the CA server's details as well as the certificate. Now the other device has got a cert. At that point, you can now authenticate one another using digital certificates. The names of these are called identity certificates, which is important to remember. Opposed to what? What's the other type of certificate for all this to work? Starts with the R. For us to install this identity certificate, we want to verify the digital signature, which happens with the CA server's public key. It's like, why would I have the CA server's public key? Because I installed the root certificate. The root certificate just says, I'm going to trust this CA server to create more certificates. Things that they sign, I'm going to trust. So each host that's going to participate in PKI needs a root certificate, and then once it has that, it can get an identity certificate. Once it has an identity certificate, it's like you or me meeting each other out on the road. Are you really Amin? Are you really Network Guy Dave? Are you really George? And we go, yeah, look, here's my identity. And we look at the card, it looks valid, and we go, okay, you are who you say you are. If you ever want to do EAP TLS, remember this term? This is used in 802.1x. So if you're logging onto a network with wired or wireless connectivity, that's what you're using. It's .1x. Now, EAP MD5 could be attacked because it was MD5, it was weak. EAP TLS is recommended, but it requires digital certificates to be everywhere. People cringe at that idea. But if you look at this, it's really not too bad. That role of being a CA server is something that you can add to a Microsoft Windows server. It doesn't cost you any money. Just turn it on, voila, you're a CA server. Everyone has to install your root certificate, but once they do, they will accept any certificate that you sign. That's a big thing to understand. See, if I told you that I was a CA server and you should trust me, and you go, okay, sounds good, I'll trust Ryan. Well, now if I make a certificate and I say that I'm eBay or PayPal or Bank of America or Coinbase, and I present that to you, you would trust it. You would get a verified logo. You'd get the little lock in your address bar saying that you're really connected to the right site. This is what we do for SSL decrypt. we basically inject ourselves as a CA server, sign a certificate, and now we can decrypt people's traffic. No questions yet in room chat. Everybody doing okay? So zero trust is an old concept in my mind, which was principle of least privilege. When people talk about doing zero trust, a lot of times it ties into many different aspects. Let's come over here. Let's start with NAC, or Network Admission Control. If we're using Network Admission Control, or 802.1x, what we're basically saying is that every port is unauthorized. So we're like, yeah, Dan's here. We like Dan. We can trust him, right? How do we really know it's Dan? So as soon as you come into the network, you're like, hey, I want to do DHCP. How about that? The switch is like, screw off. EAP only. The only thing that this switch wants to hear from you is EAP traffic. It won't do DHCP request. It wants to know who you are before it does anything else. Now this EAP process, it's a layer 2 authentication mechanism. You're going to put in credential details, pass them to the switch. The switch is going to relay this using radius to something like ICE or Forescout. This is a policy server. Now, when we talk about zero trust, it a lot of times ties into this whole process. See, when you're authenticating to come in the network, you're like, hey, this is who I am. Well, great. I know your password. Maybe we did multi-factor. I know that it's you. But what comes next is all the policies. And the policies define what it is that you can do. And we go, okay, Dana's here. It's definitely his password. What can he do? And we go, wait a second. It depends. You're like, why does it depend? Depends because we have policies. And what we can do is we can have a longer conversation. So I can go, okay, it's great that it's you. Those were your credentials. How is your, and they'll call it security posture. How's your posture? Are you standing up straight? And what they're asking is, do you have the latest operating system update? Do you have the latest antivirus signature pack? Is everything, do you have a software firewall that's running? So security posture is basically checking the endpoint to make sure that everything looks good. We can also, we were talking about digital certificates. I mentioned this yesterday. You have a digital certificate for a user. You can have another one for the machine. Which, if you've got a machine digital certificate, I'm like, man, this is Dan, and it's definitely Dan on his corporate issued laptop. That looks pretty good. Next thing I can do is look and make sure that you're patched, you're up to date, you've got antivirus running, you've got your software firewall on. If all that looks healthy, that's our posture check. That's going to come into ICE. And what's so cool about this is there's something called a change of authorization. Remember, we said this is a AAA server? Authenticate, and once we know who you are, we can authorize you. And once we authorize you to do things, we've got accounting records of what you've done. So change of authentication, or change of authorization, as it's called, COA, says, okay, Dan authenticated, and we knew some things, but we needed to find out some more. Or maybe you hadn't patched yet. Your laptop's been off for a week. So we put him into a quarantine VLAN. He updates. He communicates to the policy server that he's updated, and this change of authorization says, you know what? Let's alter his VLAN. He was in VLAN 99, which was quarantined before. We're going to move him back to VLAN 50, which is for our lab development. So we can dynamically allocate VLAN assignments and access lists to these ports, and then as the host posture changes over time, we can update that. It's really pretty cool. ICE is responsible for speaking to your switches and your infrastructure through radius, but you can create third-party connections to ICE. So if you look at Rapid7, these are the guys that create Metasploit. They've got a program called Nexpose. Nexpose is their vulnerability scanner. So just to kind of take the story a little bit further, and we'll wrap it up. If Nexpose is scanning your environment and it discovers vulnerabilities on a system, it will tell ICE. ICE is like, whoa, that's no good. That's a critical vulnerability on that system over here. ICE logs into the switch, tells the switch to block that particular port, and you're offline until you get patched. Really pretty slick, huh? So we can do quite a bit of dynamic interaction with the way that the network behaves, and based on your security posture. We can start off with very little, and we go, you don't even get a DHCP address until we know who you are. And then as we know who you are, as we pay attention a little bit more, we can give you a more appropriate level as conditions change. Pretty neat. Ooh, VPN Essentials. And how are we doing on time? 8:33. All right. So let's talk about encryption for a bit. VPN Essentials, IPsec, and we did a little SSL. So let's just start off at the very basics, encryption versus hashing, because I'm not sure who was here the last couple nights, and sometimes these are easy to get mixed up. Remember, these both kind of fall under the umbrella of talking cryptography, but they do different things. One is no more important than the other. They kind of like one hand washes the other. Encryption's goal is to give us privacy. Hashing's goal is to give us integrity. So the way that this is achieved is hashing will take variable length input and create fixed length output. It's kind of funny. Variable length input creates fixed length output. When I say variable length input, you can take a file of any size. What do I mean any size? It could be like 8 bytes. I don't know if a file can even be that small. But let's say it's an 8-byte file, or it could be 8 terabyte file. And when you run it through a hashing algorithm, the output is always the same. So variable length input, when run through a hashing function, creates a fixed length output. So just to do an example, MD5 is still a very common hashing algorithm. You could take Ryan.txt, which is just a text file with the name Ryan in it, or you could take Ryan.back, which is just a 4 terabyte backup of my computer here. If I run either of these files through MD5, it's going to create a 32 character checksum. It just looks like 32 characters of gibberish, almost like a CD key. Yeah, math fun. This is called a digest. There's no way ever to take a digest and reverse it to the input. Hashing's a one-way function. And you contrast that with encryption because this is a two-way function. We encrypt and we decrypt, but hashing is always one way. So one way that I sometimes describe this is I say when we take a look at hashing, think about going to Publix. If I went to Publix tonight before class and I bought $104.87 worth of groceries, how much did my groceries weigh? Like, I don't know. Like, how many items did I buy? Go, I don't know. And I go, but if you had every single item there, could you add them all up and get the total again? And you say, well, yes, absolutely. That's the concept of a digest. There's no way to take $104.87 and go, what on earth made this? But if you take the right input and you add it all up in the same way, you'll always get the same output. So when we look at data, if we've got a very small file or a very large file, when we run it through a hashing function, it will always create the exact same output. Now, if this file here, the Ryan.back, if this is 4 terabytes, remember there's 8 bits in a byte, so this would be like 32 terabits of data, if you can imagine that. If I changed one single 0 into a 1, The checksum here, this 32 character checksum, looks like a CD key, is totally different. It's been completely altered. And they call that an avalanche effect. The purpose for that is that if there is a change, if something is corrupted, we can see it visibly immediately right away. It's not like you're just trying to pick out the one bad character in 32 characters. So the function of this, once again, is integrity. It's a one-way function. If you have input, you can always create the output. When we do password cracking, this is what we do. A digest is also known as a hash. So if somebody gives you a hash, and you're like, where'd that come from? And you're like, Red Hat Enterprise Linux. I go, oh, I know what hashing algorithm they use. And what you'll do is you'll take every input in the universe, start with dictionary files, move over to brute force, and you say, what possible series of letters will create that hash? And once we find it, we've broken it. But we crack hashing by trying lots and lots and lots of different input and then creating the same output. Let me know if that made sense to you. We'll tackle hashing and make sure it's 100% before we get into encryption. If it looks good, you can just say, looks good. And if not, let me know that too. And I'll just chat while I'm waiting for answers to come in. Sometimes you can pull known good hashes, and then you can compare known good hashes to files on your file system. There's been a file-based intrusion detection system for years called Tripwire that just looks at all the files in your file system, makes hashes, and if any file changes, it can notify you to that. All right, John says looks good. My channel says looks good. Fantastic. That's 100% looks good. George too. Still 100%. Cool, we'll get into the encryption side of it then. And I'll actually get a fresh whiteboard for this. So when we look at encryption, there's two types. Symmetric and asymmetric. Symmetric is the same key on both sides. Whatever you encrypt going in comes out the same way. This is 5,000 years old. Asymmetric encryption has only been around since the 70s. So this is about 50 years old. It's a long way off. But the big deal about these and why they're different is with symmetric encryption, which we've had since the dawn of time. Say that you've got some emperor or king, they want to send a message somewhere. You take the message, you need an encryption algorithm, you need a key that goes with it, and this is going to produce ciphertext. The ciphertext needs to be sent somewhere. So maybe I write it on a parchment, maybe a stone tablet, I encode it, I do whatever I need to do, and I send it to somebody. Well, if I sent the key along with it with the same messenger, when that messenger gets kidnapped, there goes all my data protection. So for years, and when I say years, 5,000 of them, some of the most powerful people to ever inhabit this planet have had key distribution issues. How do you get the key to the other party without it being intercepted? Do you send it over there and do you get the key to the other party first and then encode your message? Because one's no good without the other. And there have been some really wacky things that people have done over the years to try to transport keys securely. Symmetric encryption's great. We use it all the time. We use it to this day, but we still struggle with key distribution. So when asymmetric encryption came along, they solved that problem. Because, I mean, imagine if I'm in China and I don't trust any of the equipment around me, how do I encrypt something and send you the encrypted file? That's easy, but how do I get you the decryption key? I can't text it. Our US government's talking about looking at SMS text messages now. So text isn't secure. Email's not secure. How do I get the key to the other side in a secure mechanism? Am I going to mail it? Is the mail secure? it becomes quite an issue. So about 50 years ago, RSA, Rivashavir and Adelman, came up with asymmetric encryption. And when we did, we're like, hey, look at what we solved. The Brits were like, cool, you guys are doing that too now? Because GCHQ had already developed asymmetric encryption but hadn't released it to the public. So when RSA did, the whole world started using it. And the advantage to this is that you have two keys. You've got a public key and a private key. They're mathematically related. Whatever is encrypted with the public can only be decrypted by the private. Whatever's encrypted with the private can only be decrypted by the public. Kind of funny, kind of weird. But what this does for us is it solves that 5,000-year-old problem of key distribution. I could be in China, I could create a pair of RSA keys, I could send you the public one. Who's allowed to know my public key? Everybody in the universe. Now the way that this works, what's so slick, is if you want to encrypt a message and send it to me, you encrypt the message with my public key, and who can decrypt it? Only the person that has the private key. So this is how encryption works. I'm going to tell you one more time. To do encryption, send other people your public key. Everybody can have this, everyone can know it, and whatever's encrypted with your public can only be decrypted by the private. That is encryption. Now there's something else called a digital signature, which everybody has heard of but may not understand. So let's talk about it. If I encrypt something with my private key, anyone with the public key can decrypt it. One more time. Anything that I encrypt with my private key can be decrypted by my public. Who has the public key? Everyone. So if I want to keep things private, would I encrypt them with my private key? No. What the private key is for is a digital signature. If I just released a DLL, and I said this DLL will allow Wireshark to leverage your GPU. It's a new library that does crazy stuff. But you're like, wait a minute, couldn't a DLL do something really nefarious to my computer? I go, it could, but this one is trusted. You go, how do you know it's trusted? Well, I take the DLL and I hash it. What's that give me? A digest. I take that digest and I encrypt it with my private key. So digest plus the private key is going to equal ciphertext. I give you the DLL and I give you ciphertext. What do? You use the public key against that ciphertext and you decrypt the original hash. Well, if you use the same hashing algorithm, let's say SHA-256, against that DLL, it creates a hash. If these two hashes match, A, integrity is proven, the data hasn't been altered, but B, you know it really came from me. How do you know? Because there was a hash of this exact file encrypted with my private key. Only I could build that particular cipher or digital signature or digest. Who can verify it? Anybody that wants to with the public key. So this is used all the time when you do updates like through the App Store or you download packages. A lot of times this is being used to verify that your device driver has been digitally signed or your software update has been digitally signed. Looking at the diagram, looking at time, thinking about the direction to kind of take this. At this point, we should have an understanding of asymmetric versus symmetric. Asymmetric uses two keys, symmetric uses one. Symmetric is very, very fast. 1,500 times faster than asymmetric, they say. It varies based on a lot of different factors, but it's drastically, drastically faster. Why is it so much faster? Look at the key size. When we do symmetric encryption, your keys are 128 to 256 bits. Again, it's 2 to the 128th. It's a big number. But when we look at asymmetric, this is 2048 to 4096 typically. And again, this is 2 to the 4,000th power. So you're talking about just like an ocean of key space. This is very, very complex mathematics. Again, that's why I said that this is very slow. It's heavy. So in reality, we don't use asymmetric encryption for a whole lot. We use it to verify things are digitally signed. We use it for, get this, key distribution. If I want to get the key to the other side, a key is not very big, it's just a password. I'll go ahead and use asymmetric encryption. Once that key is on the other side and it's set up, I move over to using symmetric encryption. So it's not like you have to look at these and say one is bad, one is good. They just do different things differently. So for bulk data, like for a VPN, and I've got I can write that better. I got to work on my handwriting, guys. For bulk data encryption, symmetric is king. It's so fast, it's so slick, it just rips. For key distribution, for authentication, asymmetric encryption is the best thing in the universe. Because before it existed, we really had some problems here. But in most scenarios, you'll probably want to distribute keys, you'll want to authenticate, and then you'll want to get into doing bulk data encryption. So you'll use both of these. How is this stream working for everybody? I keep getting these like little loading logos on my interface, but I hope the connectivity is good. It says it's an excellent connection, but it looks like it's buffering in my little preview window. And along with letting me know how the network connection is doing, also let me know if you've got any questions on symmetric versus asymmetric encryption. Symmetric, you're going to see triple DES. Let's see, DES was 56-bit encryption. Then you had triple DES, which was 168, but not really. AES is what we use today, which is 128, 192, or 256-bit. And then on the asymmetric side, we do RSA and DSA. Just give me a second here, guys. My looks like my YouTube interface is freezing up. Yeah, super frustrating. YouTube's not loading. I think my stream locked up. Plenty of disk space. I think I got plenty of memory. Plenty of memory, plenty of disk, 1% network. Yeah, I'm not sure why it's being so goofy. I'm going to reboot, and I'll try to be right back. Sorry for this, guys. Hope this fixes it.